a few applications in the area of computer vision, a few purely MNIST dataset execution, along with some real-time projects, Google autonomous vehicle. See, Madam, yesterday this is the updation. So I would like to thank you, Madam, for accepting our invitation and continuously. Yes. Now I request Professor Sasi Madam Garu, please accept and continue the session. I request participants, please give me a applause.
Good morning, everybody. Good morning. So, it's almost a continuation for what Professor Bari Madam has discussed in the yesterday's session on deep learning. Broadly, we have in deep learning the feed-forward network architectures with many hidden layers so that it becomes deep. And then the CNN architectures where you can grasp the features from the input in a hierarchical manner through multiple layers of the convolutions followed by pooling. And then you will have a different architecture for deep learning known as RNNs, that is recurrent neural networks. In today's session, I'll be covering, the first session I'll be covering the RNN, and in the afternoon session I will discuss the transfer learning towards NLP. So these are the topics we'll be discussing. Enables computer vast experience. Unless you have abundance of data, you can't proceed for deep learning. And it enables understanding the world in terms of hierarchy of features. This feature hierarchy, that means learning features which are complex in terms of features that are of less complexity. And again, the features of less complexity will be learned as a combination of features which are very, very simple. So that is a feature hierarchy. So deep learning requires multiple layers because it aims to learn feature hierarchies, especially in the domains where complex features will be there, like understanding the image and automatically generating the caption for the image. So in order to generate the caption, that means what it does says, you actually have to understand the contents of the image. Okay? So it's not just a segmentation or something like that. So for all that, you require hierarchy of features. Deep learning architectures build high level abstract features in terms of simpler features. Okay? This is what it is exclusively used, extensively used to learn the feature hierarchy through standard layers of hidden nodes. Of course, vast experience. Now, because you are already familiar with CNN, let me start from the next level. After looking at the limitations of CNN. So, the CNNs are specialized neural networks to extract complex features from grid structured data. So, if the image is given, which is grid structured, which is nothing but the pixels in the grid structure, arranged in the grid structure. So, from there, you will be learning small edges and then some contours and then some features of objects, and as a combination of features of objects, you will be finally able to identify the faces. Okay? So, like that, it is a hierarchy of features learned by the CNN. They are specialists on it. It scales to very large size due to parameter sharing among the subjects. Because parameter sharing and sparse connectivity, these are the two aspects that makes the CNN much more efficient compared to the feed-forward neural networks dealing with grid structure and it will be able to get the essence of the image much faster and more efficiently. CNNs process data part by part in a fixed length window, whereas the features from sequential data are spread over dynamically changing window sizes. So, this is a requirement from the image. In order to process the sequences, you require the windows of varying sizes. Whereas CNN is processing the data in a fixed sized windows. Okay? That is one of the bottleneck of CNNs when you try to apply CNNs for you require sequences for dealing with for extracting features from sequences of varying length. Similarly, features of varying lengths. Hence, CNNs fails to capture the inherent features from sequences, especially of unknown lengths. So, you require a image of fixed size, then CNN will be working well. How important is it to deal with sequences? Nowadays, there are so many domains where you will get sequential data. Starting with the speech, I am talking to you. So, it is a sequence of phonemes. So, it can be of varying length. It is most of the times it will be of varying length. Okay? Similarly, the weather parameters recorded periodically at a location. So, you can have at every half an hour the weather parameters like the temperature, the wind velocity, the atmospheric pressure, the humidity, etc., will be automatically recorded and maintained. So, this is a continuous sequence. Okay? So, that also generates the sequence of sequence data. Next, the words. If you are dealing with text, the natural language text, it is a sequence of words. Now, again, it can be, the text can be again structured or semi-structured. It can be a sequence of words, and sequences of words will be forming sentences, and sequences of sentences will be forming paragraphs, and sequences of paragraphs will be forming essays. Like that, it goes on. Next, the sequence of events recorded in a observatory. This is also another source of sequence data. Next, the stock market data showing the data fluctuations, and then data recorded in the sensor networks. This is also another regular source that provides a lot of sequential data. Similarly, the IoTs nowadays are becoming very popular, and the health informatics is again another domain where you get lots of sequential data. When you are monitoring a patient, you have to record the readings continuously as the time goes on. So, these are all various sources of or various domains where you can get sequential data. Next, modeling the sequences. The feature or pattern extraction from sequences is modeled as a dynamic system in a state space driven by an external input. Like you might be remembering the HMM. You have a external input, and to that stimulus there will be some response either by changing the state, or in addition to change of state you may have only also an observable output. Okay? So, that is all called a dynamic system, and from this you need to extract the patterns. At a given time, the output is a function of the present input and previous state. So, because it is a sequential stimuli, you will be receiving stimulus one by one, and for each stimulus you will have the state change resulted. Okay? So, whether the output is observable or not, the system changes from the previous state to the present state upon receiving the input stimulus, and then the behavior of the system is represented by a set of parameters. Anywhere throughout the deep learning or machine learning, always the theta is the famous theta that represents the model, because it is a set of parameters that defines the model. Whenever you see theta, it is a model. Okay? So, now the RNN operate on a sequence that contains vectors xt. You need some terminology. So, xt is the input at time t, okay, at time step t, and the sequence will have several xt's, t varying from 1 to tau. Okay? Then you will say the length of the sequence is tau, and tau can vary when your model is able to, it is capable of dealing with varying length of sequences like the speech signal. It is a varying, different songs, music, it is a sequence of notes. Okay? They obviously will have varying lengths. Okay? So, depending on that, tau represents the length of the sequence, that is each sequence is a input and a specific part of it is xt, that is the input at time t, okay, for all t starting from 1 to tau. Next, RNNs work on mini batches of sequences of different taus. For each member of descent is estimated by selecting probabilistically at random or some of the training examples, and on those training examples make an estimate of the gradient. What is a gradient? Gradient is the rate of change of error with respect to weight vector, that means each component of the weight. So, accordingly you will have a estimated gradient descent. So, it is a efficient way so that you can finish the weight update much faster if you go for stochastic gradient descent instead of the actual gradient descent. If you go for actual gradient descent, every time you have to experience the whole set of training examples. So, we will go for mini batch. Mini batch means a small subset of the whole training examples, and based on the subset you will make an estimation of the gradient, and accordingly we will make the update, weight update. So, here when it comes to the mini batch has a small set of, say if the batch size is 16, then 16 sequences will be taken. Okay? Each sequence can be of varying length. Okay? So, it is like Sequence is like the description of a entity, one description. But the difference that has to be noted is each input in the feed forward network or the CNN are of equal size. Okay? They are the descriptions. If it is an n tuple, n features will be there. Each entity will be described in terms of exactly n features that will be fed as the input layer, fed at the input layer. Whereas if it is a sequence, it will be of varying length, the tau varies. Okay? So, the t may sometimes refer to the position in the sequence. The t need not always be the time only, but for convenience we will say t, t plus 1 are being called like the next, the previous, etc. The next means even if it is the next in the position structurally, if it is the words in a sentence, all of them you can see them, there is no time gap in between the words of a sentence. So, it is an order which comes first and which comes later. So, next is the RNNs may be applied in 2 dimensions. It can also be applied in 2 dimensions. Okay? Again, if the data is a spatial, you can apply along the longitude and latitude separately, or if it is a sentence from left to right and right to left separately, like that you can apply the RNNs. So, when you are modeling the sequence, so if you take this one, it is a state at time t. So, it is having xt as input and then the previous state, that is s of t minus 1 is a previous state. Both of them are given as inputs and accordingly the next state will be generated. So, this is represented as s of t is equal to f of s of t minus 1 and xt, and theta is the parameters of the model. So, as I am saying, the RNN can deal with varying length of sequences with a single model. How is it possible? Because of this way of modeling. So, the same function and the same parameters theta are shared at different positions in mapping the next state in terms of the previous state and the present input. Okay? So, when the recurrent network is trained to perform a task that requires predicting the future based on the past, the network typically learns to use S of t as a kind of lossy summary. What is S of t? It should learn the gist of all that had happened previously. Then only this way of modeling makes sense. Okay? If at all the ST is a lossy summary, it can capture the lossy summary of the task relevant aspects or the past sequence of inputs. So, whatever has happened, that will be the summary of it will be captured by the S of t minus 1, and the present input, that is xt, will be given in addition to the summary of the past happenings, and then finally depending on that the response will be given by the RNN. Next, this summary might selectively keep some of the aspects. So, when you are taking the summary, some of the aspects may be given higher importance and some of the aspects will be given lesser importance based on the impact of such things for determining the next state. So, that is the attention that needs to be given for different words. when you are working with NLP. We will be discussing it in the next session. So, here this is the way a circuit diagram can be given, and in this circuit you can see this is a circuit diagram. So, each component in the circuit diagram will have a code that needs to be implemented while you are coding. Okay? The circuit diagram represents one node for each component that might exist in the physical implementation of the model. Physical implementation is nothing but, because it is a software, it is a code. The network defines a circuit that operates in real time with physical parts whose current state can influence its future state. So, here this black square indicates the delay. A single time step delay will be there. That means the previous hidden state will be inputted again to the same node. Means the present hidden state. Why are you calling it as hidden state? Because in the neural networks, the state information cannot be whatever is the entity that cannot be seen, that is unknown to the external user, will be handled in the hidden layers. So, here in this particular RNN context, the state information is not seen. So, that is referred to, that is often represented by H. Okay? So, this is the hidden node H that handles the state transitions in the sequence of time steps. Next is the size of the unfolded graph depends on the sequence length. So, here this is the unfolded diagram for this circuit diagram. When you are implementing, actually you need to implement this circuit diagram, the components of the circuit diagram, and when you unfold it for all values of the time or the positions, depending on whether you are dealing with a temporal sequence or a ordinal sequence. Okay? You will get the individual columns. Next, the hidden units of the neural network. Yeah. So, merits of unfolding the recurrence. So, the summary of the arbitrary length sequence, the summary of the arbitrary long sequence is often represented by a fixed length vector H. This is the advantage in modeling, making use of the f of H of t minus 1 or S of t minus 1, whether you refer to it as H or S, in addition to the input. Okay? So, here the H will be the fixed length vector that captures arbitrarily long sequence that is already processed at any time t. So, to predict the next word given a sequence of words, storing recent state information is sufficient. The learned model F always has the same input size rather than specified in terms of variable long history of the states. So, here always it will have the input xt and then the state information, both of them are of the fixed size. So, the input is always 2 vectors, and it promotes parameter sharing with the use of same transition function at every timestamp. I told you in the previous slide itself. That means because of the parameter sharing, you are in a position to gain efficiency in learning the parameters. As you require to learn more and more parameters, you require more data and then more time. So, always parameter sharing is preferred, and especially for RNN and CNN, they gain efficiency through parameter sharing. So, the next is recurrent hidden units can be seen. So, this is the diagram. the circuit diagram, the details like it starts with an input node and then there will be a weight vector u. So, the input will be multiplied with the weight vector and then before it gets fed it, you will have another w vector, okay, with which the previous state will be multiplied and then these two will be the inputs for determining the next state at H node. And once the next state is obtained, again you will be using a set matrix of parameters represented by V. These capital letters U, V and W, they are the parameters, each one is a matrix of parameters. Okay? So, here, so based on this, based on the state and then by applying the V on the output, the state, you will get O value and this O value is a linear summation. And for this, if you apply sigmoid or something like that, you will get the estimated value of this y. So, this estimated value of y and the actual value of y, what is y? Y is the outcome. So, they will be compared in order to find the likelihood or the loss function. Okay? If it is a likelihood, you have to maximize it. If it is a loss function, you have to minimize it. Okay? So, this is the basic structure of the circuit diagram in the recurrent hidden units. So, the unfolded way is this one. So, for each layer like at T, you will have inputs taken from the previous layer, like that it goes on, whereas individually based on the input an output is getting generated and it will be compared with the expected outcome in order to get the likelihood. Okay? So, these are the equations. So, if you understand this figure, you can get the equations very easily. Here you have H and X providing inputs to this particular node. So, as a combination, as a linear combination of this H, what is this H? It is a previous state because there is a time delay unit here. Okay? So, this is H of t minus 1 and then the present input, that is xt. But as a linear combination of these two added to the bias B, you will be evaluating the value of AT. Okay? So, this is a specific component in the sequence and based on the value of the AT, after applying the tan H function, the activation function, you know what is activation function in neurons. Okay? So, this is the total stimulus and for this stimulus you will be applying the activation function in order to get the actual outcome of this particular node H. And once this is obtained, again you will be taking the linear summation of different HTs by multiplying V into HT plus adding the bias C, you will get OT as a outcome and to this OT you will be applying the softmax function so that a normalized output. The purpose of the softmax is to normalize the all possible, that means the various components of the output vector such that they sum up to 1. Okay? So, here softmax is used and when you apply this you will get the y hat t. This y hat t gives you the probability of a specific outcome. Okay? So, that is how in this whole process what is to be learnt? It will be these vectors u, v and w with which you need to take the linear combinations and then the biases B and C. Okay? So, these will be the parameters that needs to be learned based on the contents of the training example and once those values are learnt, what is the basis for learning them? You need to maximize the loss or maximize the likelihood or minimize the loss. Okay? So, that will be the criteria. So now there will be different contexts where RNN can be used. You will start with the RNNs that produce an output at each time step. So for each x there will be a corresponding output and have recurrent connections between the hidden states. That is what a regular one we have seen in the previous slide. Okay? So here for every input you have the corresponding output produced, and in addition you have a recurrence between the hidden units. So that is one model. The next model is, there is no restriction that all RNN should be of that same type. There are several variants of RNNs. Okay? So the RNNs that produce an output at each time step and have recurrent connections only from the previous output unit to the present hidden unit. So this is more scalable. Previous one is more exact, whereas in order to gain time and reduce the memory requirements, you can parallelize the process of weight updation by going for the second option. That means you will be taking anyway, because you are generating the output for every input. You have the predicted output and take information feedback from the predicted output. So that is the second option, the previous output unit to the present hidden unit. That is the next option. And the third one is the RNNs that read entire sentence to produce a single output and have recurrent connections between the hidden units. So this is a third option. Like that, multiple variants will be there. The RNNs with output produced at each time step. What are the limitations and capabilities of it for each of these models? They are useful when y values are conditionally independent of each other given the x values, because here in this diagram, based on the x you will be getting the y, and then you are not taking the values of y at t minus 1 as a feedback to produce the y value at time t. So this holds good. This type of design pattern helps when there is a conditional independence, the conditional independence between each component of the sequence. Okay? So the next is, such RNNs of a finite size is universal, as it can compute any function computable by a Turing machine. Theoretically it was proven that if you are having the recurrent connection between hidden units to hidden units, it is universal in the sense that any function that is computable can be implemented using such RNNs. So next is, the hyperbolic tangent activation function is used for hidden units and softmax function for post processing the unnormalized output of the different classes to get the normalized probability. That is what we have already seen in the previous diagram. So two types of non-linearity is introduced on the linear combination of the inputs after applying the matrices, that means the matrix multiplication with u, v and w. You will be using tan h for state transitions, tan h for hidden units or state transitions, and then softmax for output generation, because you require a probability of each outcome. Okay? So now coming to the loss, how do you estimate the loss? The input sequence x is mapped into the output sequence y of same length in this case. For every input component xt, you are generating yt. So in this, total loss is the sum of individual losses. When you are measuring the loss in terms of cross entropy. Okay? So here the loss is expressed as a function of the inputs and the given the inputs and the outputs. That means this is the sequence of length tau, and this is also a sequence of length tau, and now you will be estimating the loss, total loss, as a summation of losses in generating individual tokens for all t starting from 1 to tau. Okay? So here this can be given as the negative summation of log, that means minus of the log of the probability by applying the model. Okay? So in order to predict, that means in order to estimate the conditional probability of yt given the sequence up to t. So it is a unidimensional because the state is capturing state st or ht, whether you refer to it as st or ht. It captures all the input, the essence of the input up to t minus 1. Okay? The state information captures all the essence of the input up to that time. So when you are taking st minus 1, it captures the information up to t minus 1, and in addition to that you will be given the xt. So it will be the xt in addition to the remaining things given indirectly, and based on this you are estimating the probability of the next output symbol, that is yt, and how likely it is. That means the cross entropy is nothing but you will rely only on what is to be produced and look at the probability with which the model has predicted it. That is why you are taking it. What is yt? Yt is the desired output at time t. Okay? And the probability with which the model has predicted the desired output. Okay? That only matters. So in order to, this is actually a pi function that will be converted into the sigma function by going for log, okay, for the probabilities. So the log of the probability of the desired outcome given the input up to time t, like that you have to add for all values of the t starting from t is equal to 1 to tau. Okay? Because the probability is going to be a fraction, you are going to get a negative value, and that negative value will be nullified by having a negative in the beginning. That is a log likelihood, negative log likelihood. So this is the function used to estimate the loss. So when you are using that circuit, then you have to apply back propagation through time, which is expensive in terms of CPU as well as memory. We will see why. So the gradient computation involves performing a forward propagation pass followed by a backward propagation pass through the graph. So when you unfold the graph, you have seen the unfolded version of the graph. So in this, in the forward direction, you have to propagate, involves performing a forward propagation pass followed by a backward propagation pass through the graph. In the backward direction, the gradient will be moving, whereas in the forward direction, the state changes will be moving. So in order to calculate the gradients, you have to finish a sequential move from the first t is equal to 1 to t is equal to tau, and then tau minus 1, tau minus 2, like that until t is equal to 1. You have to go in a sequential manner. So the runtime is order of tau and cannot be reduced by parallelization. since the propagation is inherently sequential. So this is the biggest problem. The propagation itself is inherently sequential. So you can't avoid that. That is the problem. So the states computed in the forward pass must be stored until they are reused in the backward pass, and hence order of tau memory is also required. Okay? So because of this, it is going to be very expensive. So the RNN with recurrence between hidden units is expensive to train, but it is very, very powerful. Why it is powerful? Because it is universal. Any function that is computable by a Turing machine will also be computable with this model of RNN. So we will go for a compromise. So when you go for compromise, it is less powerful. Obviously, we will compromise for a less powerful RNN with recurrence connections between, okay, it is less powerful than or compared to the RNN with recurrent connections between the hidden units. Now instead of having recurrent connections between hidden units, now you have recurrent connection between the output unit that is generated in the previous time instant to the hidden state. So even now you have recurrence, but you are taking the feedback from the output that is generated. Why? The output is anyway related to the previous state. So but now advantage is you don't have to explicitly store the previous states. The output is already available. Okay? So now you have alleviated the condition that is insisting on sequential propagation of the gradient while doing the gradient propagation in the backward direction in the back propagation algorithm. Okay? So what you can do is, you can parallelly or simultaneously, you can estimate the gradients at a different times instances. We will go for that. So this is another, yeah, this is it. Okay? So the previous model requires you to make change, that means to store the states sequentially, and while coming back also you have to go in the same sequence starting from t is equal to tau to t is equal to 1. So such a restriction will not be there in this case if you go for taking the feedback from the generated outcome to the, in order to generate the next hidden state. So the next alternative, we will have the discussion in the next slide probably. So the other design pattern for the RNN is, it is a sequence input and single output. You can see only one output is there and there is a sequence of input sequence is there. So by looking at the whole of the sequence, you will be, the system will be responding with a single output, like a reviews, finding the sentiment of a review. So after reading the whole sentence, whether the review belongs to this state or that state, we will say something like that. Okay? So it can be used to summarize a sequence. So a whole of the sequence can be summarized and it can be represented with a fixed length output. If you do that, it can be used as a pre-processing technique to produce fixed sized inputs when the original inputs are of varying size. Okay? Say when you are comparing different musics. So the length of the note sequences will be different for each rendition. So, in order to compare them, you can have, the first thing you need to do is, you have to reduce them such that they will have nearly equal length. Okay? So, that can be done as a, this model can be used for reducing the size in order to get fixed sized inputs to be processed by maybe a CNN or something like that, which are not capable of processing varying length inputs. Okay? Some models will not be capable of handling varying length inputs. So, for that you need a pre-processing thing, because the task involves varying length sequences, and unless you convert them into fixed length sequences, the next model may not be able to handle varying length input sequences. In that case, you will be going for this model. So, in this model, what is happening is, you have the sequence of the hidden states getting generated, and after processing, the whole of the input sequence, that is x tau, is fed. Then the h tau indicates the complete state description, and based on this description only the output will be generated, and this output, the O tau, when applied through, when normalized through the softmax, will be compared with the estimated y, the desired output, in order to get the loss function as we have done previously. The loss function estimation is same. Okay? So, the next is, the last model will be the teacher forcing in RNN with output recurrence. So, in this case, you have two models, one for encoder and another for decoder, or training time and testing time. So, in the training time, especially in the supervised learning, you have labels of the sequences available. So, when labels of the sequences are available, instead of giving the generated output as a feedback, as we have done in the previous case, here what you are doing is, the generated output is being given as the feedback for the hidden state. Instead of that, you will be giving the desirable output of the previous state as an input to the hidden state. So, the recurrence is given from this. So, this will give a better value, because this is more correct. This is given as the feedback. So, in this case, you can do it in a encoder decoder situation. For the encoding, you can do it because you have information about the labels of the sequences. But when you are generating the equivalent sentence, when you are generating, that is decoding the essence that is received by the encoder, then you do not have access to the desirable outcomes. So, what you will be doing is, you have to rely on the generated outcome. So, at the test time, when the desirable output is not there, you will be relying on the generated output. If the desirable output is there, then you will be using the desirable output as one of the inputs for recurrence. Okay? So, the features of training RNN with only output recurrence. So, previously we have discussed the hidden state recurrence. Now, we have shifted to output recurrence in order to gain time and memory. Okay? So, here they are strictly less powerful than RNN with hidden to hidden recurrence. That is what I am saying. It is the most powerful one if you have a feedback from the previous hidden state. But it is expensive. That is why we are moving towards taking the feedback from the output. So, the back propagation algorithm through time is not required here. Okay? Advantage of eliminating the hidden to hidden recurrence is that the training can be parallelized with the gradient of each step computed in isolation. So, in parallel, simultaneously, you can calculate the gradient of each step. For all time, for all t, starting from 1 to tau, you can directly calculate the gradients if you are working with some multi-core system. You can do it simultaneously. Okay? That is the biggest advantage I was talking about. That is why we can totally go for the normal back propagation rather than through time. Okay? Next, unless the output units capture all essential information related to past for making the predictions, this method lacks accuracy. So, this is the problem. What is the difference between a state and the output? The output is something that needs to be produced and it will be checked against the desirable output. But in addition to the generation of output, that is one task, you will be gaining some experience that is stored in the form of state. Not every context will use whole of the information that is there in the state in the form of output. Only certain part of it will be given out and the remaining part of it will be there in the state. So, in such cases, because in the feedback loop, that is in the recurrence, you are only involving the output but not the previous state, you will be losing some of the past experience, some of the past information, not whole of the sequence that is read till then, the gist of it will be captured in the state, whereas you are only feeding the output which is part of the state information. Okay? So, that is the drawback and hence it is less powerful when you are using the output recurrence. So, unless the output units capture all essential information related to the past for making predictions, this method lacks accuracy because the prediction, the output's purpose is to make proper predictions, whereas the purpose of the state or the hidden unit is to capture all the essential information that was read till then. So, that is important. The state information is more holistic compared to the generated output or observed output. Okay? So, that is why there will be loss in the information that was provided for the hidden state. So, different loss estimation standards are used at training and testing time. So, here you are using one specific output and here another specific output during test time and training time. So, this is again a issue that needs to be handled. So, this issue, this specific issue of timer, okay. So, this issue will be handled by going for curriculum learning strategy. In the curriculum learning strategy, what you will be doing is, like, we start with it is to start with feeding the actual outputs. Okay? The training process starts with feeding the actual outputs at the beginning. What happens is the weights becomes tuned to the present task, and once the weights are improved, then gradually move on to the generated output values in the later stages of the sequence. When the sequence is getting processed, okay, in the beginning of the training, that means the first several sequences, maybe the training set is consisting of 10,000 sequences. So out of the 10,000, first 500 sequences will be dealt with by taking the actual outcome, by taking the actual output for the recurrence, and after that the weights will be almost stabilized. From then onwards, what you will be doing is gradually move on to the generated output. Why? The generated output is going to be fed during the test time. So to reduce the distance, that means difference between the training and the testing methodologies, what you are doing is you are going for some sort of hybridization. During the training itself, we start your training with this, the desired output, and then after the weights are stabilized, then go for taking the generated output. For the later iterations, the later 5,000 iterations will be doing this, and finally your model will be ready for testing, because during the testing anyway you do not have the desired output. Obviously you have to rely on the generated output. So like that, the curriculum learning strategy will help to overcome the sudden change between training and testing, because the same model, the model that is developed during the training period will be used for testing. Okay, that is being tested. So a smooth transition should be there in between. So that is done by the curriculum learning. Next is the parameter sharing. The RNNs assume a conditional probability distribution over the variables at a time t plus 1 given the variables at a time t, and this is stationary. This is the basic assumption that is made, because the parameter sharing means what? You are devising a function f that is applicable for all values of t starting from 1 to tau. So irrespective of the value of t, the actual value, whether it is t or t plus 1 or t plus 2, the relationship between the input, previous state put together to the output, that is the present state, or for generating the output, is fixed. That is a basic assumption that promotes the parameter sharing. Okay? Unless you make that assumption, you can't rely on a single function with a single parameter sets for u, v and w to be applied for all times throughout the sequence. Okay? So that assumption is you are assuming the stationary assumption, that the signal is stationary. The relationship between input, previous state and the present state as well as the output is stationary. Then only you can learn a single matrices values for u, v and w. If the domain is having non-stationary conditional probability distributions among the variables, the time t is fed as additional input at each time step in order to learn time-dependent model. Okay? In some cases, it will not be stationary. The relationship between the output and the input and the state is not stationary. In that case, if it varies with time, the time value, the value of the time will also be given as additional input. Okay? In addition to x, you will also give t, so that the model will be built based on the value of t also. That is how you can still make use of the model successfully. But such time dependent models have to extrapolate to predict the future values. Okay? Now determining the length of the sequence. So in order to do, because the RNNs are equally capable of handling the varying length sequences as well as equal length sequences, sometimes you would be requiring to know the length of the sequence, add as a special symbol at the end of every sequence of symbols, so that you know that it is the end. Introduce Bernoulli output to the model that represents whether to continue the sequence or not using the additional output. Okay? So, here there will be whether to continue. Bernoulli output means yes or no, 1 or 0, like that will be added, so that upon reading that you will be, the model will be knowing whether to continue, whether the input sequence is continuing or it is ended, delimiter, like that. Add additional output to predict the length itself, and then use it as an additional input to the appropriately generate the output sequence of required length tau. So, this is a special case where you require to know the length of the output sequence. So, the next is when x is a fixed size vector, you can simply make it an extra input of the RNN that generates the Y sequence. Some common ways of providing an extra input to the RNN. Previously I was talking about the length or the time in two different contexts. If the conditional probability is not stationary, then I was telling you about providing time as the additional input. Similarly, the length, how long should be the output sequence, that should be provided as extra input. So, how to provide those extra inputs? That will be done by adding as an extra input at each timestamp. So, at each timestamp you can give it, or you can give it as an initial state H0, the value of the H0, because H0 will not be there. What is H0? It is a state at 0th time. Okay? So, that also will have the same structure. In order to predict the state at time is equal to 1, because time starts at 1, it requires t minus 1, that is H0 is required. So, at that H0 position you can give this extra input or both. And then there are certain specific structures. So, this structure is having Yt of the output sequence serves two purposes. That means, it is given as an input at a time t and as a target at a time t minus 1. So, if you take Yt, it is given as input to the at time t, input to the hidden node, as well as it is also used as a target to the previous time t minus 1 while calculate and used while calculating the loss function. Okay? This type of structure, except that everything is same, you have the input, it can be an image, and the context can be captioning, automatically generating the description for the image. So, given the description, given the image x, so you will be learning the vector R, the matrix R, and then a linear combination of certain pixels will be taken, and then they will be processed at the different states in order to generate a sequence of words that are suitable for captioning the image. So, in this context, the x value, the y value at t is given as input to the state, as well as the same value will also be used for estimating the loss of the previous state. So, this is the example. Here, can you see a dog is sleeping under the bed or hiding under the bed, or like that you can write whether to use hiding or sleeping or things like that, because its eyes are open, you can say it is hiding. So, the dog is already produced. Next word can be is and then hiding, like that. You have to continue. So, in this, the previous model we have discussed will be used. So, for image captioning, RNN is extensively used, and all these captions are automatically generated. Okay, automatically generated. So, here a person riding a motorcycle on a dirty road, like that. They are very, very meaningful, and it is possible to give such captions only if the image is processed through some CNN. So, the combination of techniques will be used. CNN processes the image and identifies the objects that are there in the image, and then their positions and the sequence of the positions, the locations. Okay? So, such a sequence will give you the idea about how to generate a caption for the image. So, this has to be trained on a lot of training data. So, after getting trained on a big set of training data, the system learns to automatically generate the captions. So, when you are working with hidden and output recurrence, that means getting the recurrence from the output nodes reflected by the previous state and the output along with the present input. And then we have applications like speech recognition, handwriting recognition, and they require to predict the output based on the positions of the input sequence on both sides. So, till now we have been discussing processing of sequence in the single direction, okay, from t is equal to 1 to t is equal to tau in a single direction. But certain applications require processing the sequence from both the sides in order to understand the role played by a specific word in a sentence. You have to see what is there prior to it and after that. Similarly, in order to understand automatically the speech, you have to identify the phonemes and then the sequence of phonemes in order to form a possible word, and it differs based on the pronunciation, etc., etc., and the background noise or signal quality, etc. So, for all these, to overcome these difficulties, you require information what is prior and what is after in order to define a context. So, based on the context, you will be in a position to actually handle the input in a better manner. So, we will go for the bidirectional RNN. So, in the bidirectional RNN, there will be two hidden units, H and G. The H will be having recurrence from the previous state. The HT is receiving input from the HT minus 1, whereas there is another hidden state, that is GT. It receives input from GT plus 1. So, this is from right to left and this is from left to right. Okay? From both the directions, you need to check what had happened in order to capture the state at which a specific input, that is xt, is to be processed, and accordingly you have to generate the output. So, when you are generating the output OT, you will be taking inputs from the HT as well as GT. Okay? So, here both the HT and GT are equivalent because they are taking inputs from X and they are giving outputs to OT, except that the recurrence direction is different among them. So, the direction of recurrence is from 1 to tau for H and tau to 1 for G. Okay? So, when you consider the context in both the directions, in order to generate the output, then you will have more information that is processed and will be able to get better outcomes, especially in applications where uncertainty is there, like speech, the other things, the understanding the words in a sentence. That means the semantic, in order to get the semantics of a sentence, you have to process the words in a sentence from both the directions. So, the next is sequence to sequence architectures. So, they will, here the encoder will be there, all the sequence to sequence architectures will have the common structure, that is encoder and a decoder. The encoder processes the input. So, this is the input sequence, this is being processed by the encoder, and the encoder has developed, and encoder has generated a context vector, and this context vector is taken or given as input to the decoder. Okay? And the decoder generates the corresponding output symbols, so that for an input sequence X, you will have the corresponding output sequence Y generated. So, this is generally, it can be, the context can be the language translation. A sentence given in German can be automatically converted into English when you go for the encoder decoder architecture. Here there is no restriction that for every word there should be a corresponding word generated. There should not be any such restriction, because when you are translating one sentence from one language to the other, every word will not be literally converted into its dictionary equivalent in the other language. So, it has to be like this. You have to capture the semantic essence, and then that has to be reproduced in a different language. So, the length of the output sequence may differ from that of the input sequence. The applications include machine translation, the question answering, when a question is asked, like I think you have all experienced the ChatGPT. So, when you ask a question, it will answer by giving essays, isn't it? And speech recognition, in all these cases, you will have different length sequences will be generated in response to input sequence. So, the encoder on an RNN processes the input sequence and emits a context vector C representing the semantic summary of the input, and the decoder generates the most probable output sequence using C. We can see we have actually, as part of Japanese project, we have developed a automatic summarization. So, whenever you go for generative models, this is a must. A model will be generated automatically by synthesizing on its own. You have to make use of the encoder-decoder architecture. The decoder, from the context or the semantic essence that is captured in the context vector, you will be generating a sentence. The model will be generating the sentence. So, the applications of different forms of RNN can be, some of them are given like this. If it is image captioning, one input will be given and a sequence of words will be generated in order to give a caption for the image, like we have seen in the previous slide, one of the previous slides gives you. Then the sentiment classification, like if a sentence is given, a single polarity of the sentence will be given, whether it is a positive review or a negative review, whether it is a feedback or a review. Similarly, a multiple, that means a sequence will be given and in response another sequence will be generated. That will be the language translation or document summarization, all these things. So, when you go for deep RNN, you can include additional layers. Okay? Here instead of a single hidden layer, you have additional hidden layer, Z is also added with the similar nature. So, you need to learn more number of parameters. As you increase the layers, you require additional matrices to be learned. A matrix, say here, a V matrix is associated, suppose, then you will have U also, UV. If U is here and then a V will also be here. Additional set of matrices will be required. 2 more matrices are to be learnt. Okay? As more number of parameters needs to be learned, you require more data and accordingly additional time and computational power will be required in order to finish the task. So, here this is another way where additional layers are added for linear transmission of input. Here one more layer is added. Similarly, before generating the output, one more layer is added. Like that, all possible combinations will be there when you are going for deep RNN in the process of deep learning. Okay? So, RNN itself is a basic architecture of the deep learning, but if you are working with a very complex problem where you could not reach the required or acceptable levels of accuracy, if you are using a single layer of the hidden layer, okay, then you can go for additional layers at various stages. Here additional hidden layer. Here in addition to the hidden layer, you have the linear transmission layers. So, here again you have another additional recurrence component included in the hidden layer. All these things can be possible. So, there is another variant of the recurrent networks, that is recursive networks, wherein if there is a structure in the sequence, like if you take the a big document, a thesis, this thesis will have chapters and each chapter will have the similar structure. Each chapter will have, it will start with some introduction followed by some sections and each section will have subsections and ended by some conclusion. So, all that can be structured and within these structures, the subparts internally, you will have the sequence of words representing. So, in order to process such type of inputs, you will go for this recursive networks. In the recursive networks, you will be repeating the same task on each subtree. Okay? Each subtree, when you are dealing with a particular section, whatever you do, the same activity can be repeated on the other sections also. That is why you can go for recursive RNNs, the networks, where you can the tasks can be repeated on the subparts of the sequences. Though originally it is sequential, it includes some structure in it. So, on each structure you can do the same processing repeatedly. You do not have to consider whole of it as unconnected. Okay? So, for that. Next is, so if you do that, you will be able to reduce the time, deals with the long term dependencies better as it structures a sequence of length tau with a depth of log because when you arrange the information in a tree, the length will be reduced. Okay? The variable length sequences can be mapped to a fixed size representation. Okay? What is a sentence embedding? Nowadays, all of you are familiar with word embeddings. So, a sentence embedding means whole of the sentence will be represented as a vector that captures the semantics of the sentence. Okay? It is similar to the word embedding, but in the place of each and every word, now you will be considering a sequence of words that constitute a sentence. And next, when you go for the RNN, you have to deal with the vanishing and exploding gradients problem. This is because when the sequence length increases, what you will be doing is, you will be updating, that means the gradient calculations becomes either explode or vanish, depending on whether the original gradient is more than or nearer to 1 or nearer to 0 in the beginning. So, in non-recurrent networks, the problem is reduced by adding the individual weights of the, adjusting the individual weights of the layers to have variance distribution normal. That means around 0 as a mean and the nth root of the desired variance to avoid extremes in the weight vector at a level by level normalization. That means all the weights at a particular level will be normalized such that they will sum up to 1. This automatically imposes a restriction and avoids explosive growth or reduction of the values of the weights in the feed forward neural networks and the other situations. But whereas in case of recurrent neural networks, it is not possible. Why it is not possible? There is nothing like the limit on the specific level. What you will be doing is, the way the gradients are calculated is, it employs shared weights through series of time steps, leading to reduced weightage to long-term dependencies. Because the gradients will be multiplied by themselves again and again. As the length of the sequence increases, the values of those gradients becomes very, very minute. Okay? The situation is like when you are calculating the likelihood as a product of multiple probabilities. You will expect so many zeros or underflow on the systems. That is why you are converting it into the sigma by applying log of the probabilities. Similarly, here also, when you are multiplying the gradients in the time, as a time for all times t is equal to 1 to tau, for larger values of tau, you will end up in almost vanishing gradients. So, that has to be avoided. Okay? So, this is, it reduces, leading to reduced weightage to long term dependencies. Traditional RNN via stochastic gradient descent reaches 0 weightage for sequences of length 10 to 20 in practice. So, if you apply the normal SGD, this problem will be there. So, this can be avoided by going for LSTM cells. For state transition, extremely successful for unconstrained handwriting recognition, speech recognition and handwriting generation and image captioning and parsing. There are so many applications for the LSTM, these are only a few. It supports internal recurrence, introduces self loops to dynamically produce paths for flowing the gradients through long duration. So, here the memory, because of the memory cell architecture and because of a forget gate introduction, it decides to what extent the effect of a specific gradient will be continuing and when to stop, etc. Recurrent functions for forget gate f along with self loop wait representing the internal state of the cell and external input gate and output gate are defined for a pair of time step t and the cell I. So, given the time t and cell I, you will be having functions that define the activations of these gates, and the equations, I did not bring the equations, చూద్దాం నెక్స్ట్ దాంట్లో ఉన్నట్టున్నాయి. Yeah. So, here this is the LSTM. So, the input is here and there is ANDing with the outcome of the input gate. So, it can be either allowed or not based on the value of the input gate. Similarly, there is a forget gate associated with the self looping. That means to what extent to remember and when to forget will be depending on the outcome of this forget gate. And similarly, for the output also, once the output is generated at this stage based on the state that was generated, you will be going for the output. So, for generating the output also you have an output gate, and this LSTM has the efficiency to remember what is to be learnt, what is important, and to forget even if it has occurred in the near or it has occurred in the recent past. It will ignore such things because of its ability to forget some of the information, some of the state information, and we can see the equations. So, here there is different gates of the LSTM. So, all these gates are making use of a sigmoid function on the linear summation of the input activation xj and the hj of the previous time instant. Okay? So, here this will be used at the present state. So, in order to calculate the present state, we will use the outcome of the forget gate, and that decides to what extent the previous state is to be considered in order to calculate the present state. And in addition to that, you have the combination of linear combination, another linear combination. Okay? Here this is UF, whereas this is just U, whereas this is UQ, UG, and then this is UQ. Like that, you will have different matrices, that means more number of parameters are to be learnt, but still you will be in a position to avoid exploding and vanishing gradients by making use of these gates in coordinating the activity of the RNN. So, these are the other aspects. So, when the grade when you are having the exploding gradient means a gradient whose value is too high. In this case, the gradient is too high in this particular place. Then what you will be doing is, if you directly use that particular gradient, this is the Jacobian, okay, and if the gradient is too high at the cliffs, what you will be doing is you will go for gradient clipping. In the gradient clipping, there will be some upper limit on the amount of change that can be made to the existing weights. Because of that, the whole process will not be spoiled. So, because of the clipping, you will be modifying the weights slowly, okay, along the gradient of the line. So, here the cliffs and plateaus may result due to very large or very small derivatives of the parameter space. Cliff may cause a gradient descent parameter update to throw the parameters out of the search region. If you do that, whatever you have learned till then will be totally forgotten, and it will be very difficult. That means it is almost like you are at the first note in the game. You have to start all over again. So, that can be avoided by going for gradient clipping. Okay? So, and undo the progress made in the recent past. So, the clipping of the gradient will place a threshold. So, if the gradient is greater than a particular value V, then irrespective of the value of the gradient, you will make only a small amount of change, where G is a gradient and V is a norm threshold. Okay. So, these are some of the concepts associated with sequential pattern extraction using deep learning, and we will discuss the applications related to NLP in the afternoon session. Okay? And then in the afternoon session, I will be introducing the concepts of transfer learning, which are recently became very, very important for handling natural language and understanding the images, etc. Okay? So, with this close, yes.